Hello, in this video I'll show a deployment of model predictive control on a real laboratory overhead crane, from the problem formulation to running on real-time hardware. Here's our setup. On the left, the diagram shows a planar overhead crane with two actuators. One moves the cart along the rail, the other controls the hoist cable length. On the right, you can see the corresponding model equations. Both actuators are driven by velocity controllers, which is why their dynamics show up as first-order systems in the equations. The system has 6 states: cart position and velocity, hoist length and velocity, and the sway angle and its rate. The payload hangs freely, so any motion of the cart or hoist makes it swing, and that's captured in this last equation of motion. Now let's look at how this is deployed on hardware. On the development computer, we formulate the controller using the Impact toolchain. Impact exports this as a Simulink block, which we integrate into our real-time control diagram. This diagram is compiled and deployed onto a Speedgoat target computer. The Speedgoat sends voltage commands representing the desired velocities to the motor drivers, which actuate the cart and the hoist. In return, encoder signals close the feedback loop all the way back from the crane through the motor drivers to the Speedgoat. Here we have the MPC formulation, which performs point-to-point motions. At each time step, we solve this optimization problem over our states and inputs. For the horizon, we select 20 steps with a sampling time of 0.1 seconds, which gives us 2 seconds of prediction into the future. Since we're formulating point-to-point motions, the objective penalizes the quadratic error between the current states and a target state R, weighted by these matrices Q and QF. The last two entries of these matrices, corresponding to the sway angle and its rate, are 0. So this controller has no notion of the payload swinging at all. Let's see what this looks like on hardware. The black dot shows the position of the load based on the measurements. The green star marks the target state for the load. In blue, you can see the trajectory predicted by the controller. On the right, the plots show the control inputs over the prediction horizon. As you can see, the cart and the hoist reach their targets, but the load keeps oscillating since the controller ignores it. Now let's add the sway to the cost function. The structure of the problem is exactly the same as before, but now Q and QF also penalize the sway angle and its rate. Let's see how this changes the behavior on hardware. The starting position and target are the same. This time, the cart and hoist reach their targets, and the payload settles smoothly, without oscillating, since the controller is now actively damping the sway. You'll notice a small offset between the black dot and the green star at steady state, due to a small measurement error from rope deformation. Instead of correcting it and risking oscillation, the controller settles into a stable balance close to the target. Let's see what happens if we manually disturb the payload. As soon as the sway is detected, the controller reacts and brings the payload back to a stable position. Now let's try a different cost structure. Instead of a quadratic penalty, the stage cost here uses an L1 norm, weighted by W1 with exponentially increasing weights. This penalizes the distance between the state and an artificial reference, XAR, which is itself a decision variable. A second term penalizes the distance between this artificial reference and the actual target R, weighted by W2. There's also a small regularization term on the inputs. This L1 structure tends to produce bang-bang inputs, saturating at the limits, rather than moving smoothly. Let's see this on hardware. The starting position and target are the same. The payload still settles without oscillating through a different trajectory. Notice at the end of the prediction horizon, that is, the artificial reference, converges smoothly to the target state. Now let's manually disturb the payload and see what happens. As soon as the controller detects the sway, it responds and steers the payload back to a stable position. That's it for this deployment. Thanks for watching.